Good afternoon. Today we are going to do the density and concentration lab. Our guiding question for the lab is, how do we use the density of a solution to determine its concentration? For the introduction, we have some background information. The density of a sample of matter represents the mass contained within a unit volume of space in the sample. For most samples, a unit volume means 1 milliliter. The units of density, therefore, are quoted in grams per milliliter or grams per cubic centimeter for most solid and liquid samples. Densities are usually determined and reported at 20 degrees Celsius, which is around room temperature, because the volume of a sample and hence the density will often vary with temperature. This is especially true for gases, with smaller but still often significant changes for liquids and solids. Density can also be used to determine the concentration of solutions in certain instances. When a solute is dissolved in a solvent, the density of the solution will be different from that of the pure solvent itself. Handbooks list detailed information about the densities of solutions as a function of their composition, typically in terms of percent solute in the solution. If a sample is known to contain only a single solute, like it is today, the density of the solution could be measured experimentally. And then the handbook could be consulted to determine what concentration of the solute gives rise to the measured solution density. For liquids, very precise values of density may be determined by pipetting an exact volume of liquid into sealable weighing bottle. This is especially useful for highly volatile liquids, and then determining the mass of the liquid that was pipetted. A more convenient method for routine density determinations for liquids is to weigh a particular volume of liquid as contained in a graduated cylinder. It is this second technique that will be used in this lab. The concentration of solutions is often expressed in terms of the solution's percentage composition on a weight basis. For example, 5% sodium chloride solution contains 5 grams of sodium chloride in every 100 grams of solution, which corresponds to 5 grams of sodium chloride, and because water has a density of 1 gram per milliliter, we have 95 grams of water for a total of 100 grams. Our materials we're going to use are this is our 100 ml graduated cylinder. We're going to measure the mass of our solutions in this little 10 ml graduated cylinder. We're going to prepare sodium chloride solutions with concentrations of 5, 10, 20, and 25, and we'll be given 2 unknown concentrations. We need a digital balance and transfer pipettes. We are going to calculate the mass and the volume of water that we need to prepare our solution. So we're going to start with our 25% solution. To prepare our 25% solution, we are going to put 25 grams of NaCl plus 75 grams for a total of 100 grams of H2O. And remember that the density of water is 1 gram per milliliter, so 75 grams would be 75 milliliters of water. Okay? Next, to prepare our 20% solution, we're going to use the highest concentration, our 25, as our stock solution, and we're going to dilute the others from there. So for 20%, we're going to use this equation, which may or may not look familiar, to calculate how much of our stock solution we need. The concentration 1 is our stock solution. So for C1, I'm going to put 25%. V1 is the volume of that we need, and I don't know that amount, so I'm going to leave it as V1, that's my variable to find out. C2 is the concentration we want to get to, so 20%. And V2 is how much of that we want to prepare. Since we're going to need 10 milliliters, we're going to make 20 just to be safe and make sure that we have enough. So 20 milliliters is how much of my new diluted solution I want to end up with. So if I solve for V1, I'm going to divide both sides by 25%. And V1 is going to be equal to 20 times 20 divided by 25. And that should give us 16 milliliters because percentages have canceled out. So 16 milliliters of my stock solution, plus we are going to add 4 milliliters of H2O to get to a total combined volume of 20 milliliters that we calculated. Okay, for 15%, we're going to use the same equation, but we're going to plug in C1 is still 25. V1 is still our unknown. What I want to find is, whoops, this is not 15. I apologize, this is 10. 10%, and the volume of that we want is 20 milliliters. Okay, so V1 is going to be equal to 10% times 20 milliliters divided by 25%, which should give us a volume of half of what we just calculated, 8 milliliters. If I add 8 milliliters of my stock solution, that means for a total of 20, I need to add 12 milliliters of H2O. Okay, and last but not least, our 5% solution, that looks like an S. 5% solution, we're going to use that 25% stock solution. One more time. How much of it will we need? A very small amount because it's a very small concentration. 20 milliliters. Okay, and to solve for V1, 5% times 20 over 25. You guys should be working on your mental math here. So 5 over 25 is 1/5, right? 1/5. 20 divided by 5 is 4. 4 milliliters. And if I have only 4 milliliters of my stock solution, then the other 16 is going to be H2O. 16 milliliters of H2O. Okay, so now we can prepare our 4 solutions that we are going to find the density of. The other pre-lab question says to draw what the ions would look like. So let's look at that really quickly. If I had all these waters floating around, okay, if I have all these waters in solution floating around, what does the salt look like? Well, the salt has been dissolved, so it's separated into its ions. I'm going to draw the chloride ions as these green circles, and sodium we'll draw as a purple circle. Sodium has lost an electron, so it's shrunk in size, so it's going to be smaller. I'm just going to put a plus since I don't really have room to write Na. And we also want to make sure that these are present in equal amounts. So if this was my 10% solution, in order to draw a 20% solution, I would double the concentration, and I would need to add 2 more of each ion. Okay, and that is sort of what a diagram would look like of my ion. We're going to prepare our stock solution, the 25% sodium chloride, for the concentration and density lab. So I'm going to take my weigh dish, and I'm going to zero the balance with the weigh dish. So now that it reads 0, I'm going to add my salt to get to 25 grams. Slowly. We're at 21, 22, 23, 24, and let's get as close as we can to 25. 24.99 is pretty good. So we should record that we use 24.99 grams of sodium chloride. And I'm going to go ahead and put that into my beaker here that I have labeled with the 25. I should add the percentage on there, 25%. And to that, since we are measuring by mass, we want a total of 100. So I'm going to have 75 milliliters of water, and I'm going to pour most of it. And when I get close to the 75 mark, I'll use the pipette, since this is missing the straw. So I'm about 70 right there. Okay, 70. We're going to use our plastic pipettes for the last 5. Okay, and notice how I'm getting down to eye level. The meniscus is the name of the curve of the water. And we always want to read from the bottom of the meniscus. I'm at 74. From the bottom of the meniscus, we want that right in line with that 75 mark. Okay, and there we go. So we get down to eye level, and we want to look straight on and make sure that it is 75. Okay, and I'm going to pour that into my beaker. Okay, we're going to need to give this a good stir. Let me get the stir rod out, or we can use a scoopula as well. Let's give that a really good stir. Okay, so we need that to be completely dissolved before we start making our dilutions. Remember from our pre-lab, we're going to start by preparing the 20% and the 20% sodium chloride solution. We're going to take from this 100 milliliters that we just prepared, this 100 milliliters of stock solution, and we're going to measure out 16 milliliters. 16 milliliters of this stock solution. Okay, and I think this is going to have to be one of those things that we learn as we go. I think it's going to take a lot more stirring to get that completely dissolved. We're almost at the saturation point of sodium chloride, so it's going to be very difficult to get all of this salt dissolved in here. Okay, we're going to have to do a lot of stirring. Hopefully I can edit this middle part out. If not, you guys are just going to watch me stir for quite a while. If I pour out of here now, I'm removing more of the water than the solute, so I'm actually changing the concentration. So that would mess up our entire lab procedure, so I do not want to do that. We just have the tiniest bit there at the bottom still. Can you see it? I'm going to get it all dissolved. Almost. This is a highly concentrated salt solution. So if you've ever been to Florida, the water there, since the temperature is so high, it holds more sodium and chloride ions. So the water in Florida has a high salinity, and it's also very dense. So that should tell us something about the pattern that we're going to see for the density. It's easier to float in because the density is so great. It's much easier for people to float. All right, so I think we have it all dissolved. So now let's go ahead and prepare our 20% solution. So in the 20% solution, we are going to need, I know I just said it and now I have to look again, 16 milliliters. So I'm going to pour into here until we get to about 15. Okay, and let's use our clean pipette. Take this out. Clean pipette for that last milliliter, and we don't want to pick that up because that's going to make it uneven. Okay, so we're at 15 and bottom of the meniscus, perfect, at 16 exactly. put that in here. Okay, and while we're measuring stock solution, let's go ahead and do the other two as well. So for the 10, we needed 8 milliliters of our stock solution. So let's go ahead and pour. Oh. Okay, this should be a duh moment. We can't use this one because it only goes down to 10. So for 8 milliliters, I'm going to have to switch graduated cylinders. And I'm going to have to use the 10 milliliter one. Okay, so let's use our stock solution. We're going to fill this up to about 7. And I'm going to use the pipette for that last 1 milliliter from the bottom of the meniscus. Okay, and the meniscus is much more pronounced in this one than it was in the large one because I have such a small, a little bit too much, so I'm going to take a tiny bit out. Too much. There we go, perfect. So we have 8 milliliters. 8 milliliters of our stock solution goes into the 10. Okay, so there goes my 8 milliliters into there. And for our 5% sodium chloride, we only need 4 milliliters. So I'm just going to use my plastic pipette to add 4 milliliters here. There we go. Okay. So my 4 milliliters of stock solution go into my beaker. All right, and now I'm going to rinse this with some tap water. I'm going to rinse it with some distilled water. So there's no salt in my 10 ml graduated cylinder. And I'm going to go ahead and go back and add the water. So in my 20%, I only need 4 milliliters of H2O. Okay, so let's move this out of the way so it doesn't get knocked over. So I need 4 milliliters of distilled water. I went over a little bit. Let's take some out with this pipette. There we go. Into the sink, not back into the distilled water. And I'm going to add this to my 20. Okay. So the 20 milliliters, mix it around, is prepared. Let's do our 10. Okay, so we had 8 milliliters of stock solution, so we're going to need to add 12 to get to a total of 20. So I'm going to go back to this one. Okay, and I've used too much. I'm at 15. Since I can't take out of this one, I have to make sure that I'm under. And I'm at 11. So let's add that last little bit to get to 12. There we go. 12 milliliters going into the 10%. And I'm going to swirl that around and put it back here. It's ready to go. Okay, and the last one that we need to prepare is our 5%. Our 5% solution requires 16 milliliters of distilled water. 16. Okay, I'm at about 12 there. And 15, 16 milliliters. Okay, so my 16 milliliters of distilled water is going in. There we go. Mix that around. So now we have our solutions prepared. So what we're going to do now is I'm going to rinse this again. And when you're measuring things in the lab, Often we can reuse our equipment, but we have to make sure we rinse in between. And if we have a gradient in concentration like we do, then we're going to make sure we go from low concentration to high. Okay, so let me just dry my hands off really quick. All right, so we're going to use our same graduated cylinder that's now rinsed, and we're going to fill this to the 10 milliliter mark with our 5% solution and measure the mass of this. So we're going to know the volume is going to be exactly 10. We're going to measure the mass, then we can find the density. So I need this to be 0. So I'm going to 0 the graduated cylinder. Okay. And using my clean water pipette, I'm going to fill this up. And give it one more quick stir. Okay, so we're filling this with our water. Oh, it's not water, it's a solution. With our 5% solution of sodium chloride. Getting very close to that 10 milliliters. And we need 1 or 2 more drops down at eye level. There we go, perfect. We needed 8 more drops. So now let's record our data. So we are going to record that in the 5%, for 5% sodium chloride, it's 10.11 grams. And remember that the volume is 10 milliliters. 10.0 milliliters. Okay, right on the line. So now, because that was 5%, we're going to double the concentration. I can just dump this one out and move straight up to the 10%. I do want to 0 it again. You guys can't see maybe, but it's gone up to 0.08. That is a random error. So I'm going to hit 0 to try to control that as best as I can. And I'm going to move over. We're going to rinse the pipette with the 10. Okay, and let's fill this one up. 2, 3, 4, and 5. Okay, now if you guys noticed, I got 1 drop onto the balance. That is a mistake. That is not a random error. That is totally fixable. In fact, I wasn't going to fix it, but I am. It's a perfectionist in me, so I'm going to wipe this off. I'm going to very gently, because these are sensitive, wipe this off. Put that back on there. All right, so that little extra mass would have made a tiny difference there. And let's get this up to the 10 milliliter mark. Right there. Okay, so our 10% solution, this is looking beautiful, has a mass of 10.42 grams. Okay, and that is 10.0 milliliters. Let's do the other 2. So we're moving up to the 20%. Okay, so my empty graduated cylinder, and I'm going to rinse this pipette a little bit so I have some in there. All right. Oh, I almost forgot to 0 it. And the ant. Go. 0. All right. This is our 20% sodium chloride solution. While I'm doing this, you guys can think about how the results might have been affected if I had left that extra drop. Would the density have been too high or too low if I left the drop on the balance where it was? that would mean that the mass reading would be greater than expected. How would that affect density? Remember, density is mass divided by volume. Okay, and 20% has a mass of 10.99 grams. 10.99 grams in 10 milliliters. Okay, last but not least, check this out. And the highest concentration should have the highest density, right? That's 0. Rinse this out. There we go. 2, 3, 4, and let's get the meniscus, bottom of the meniscus, all the way up to that 10 mil mark. Perfect. Ooh, that is very dense. Okay, so the 25% has a mass of 11.55 grams in 10 milliliters. Okay, so now that we have our data, we can plug the data in and calculate the density. We are going to create a data table and insert our data from the lab. So we are going to have, let's go down a couple boxes, the temperature in degrees Celsius. Okay. We are going to have the mass, not mag, mass in grams. We're going to have the volume in milliliters. And then finally the density, which is going to be grams per milliliter. Down here, up on the top, we have our solution. So we have our 5%, we have our 10%, our 20%, and our 25% solutions. Okay, so the mass of these things was 10.11 grams. Whoops, we don't want the grams in there. Sorry about that. We already have grams over here. That's why we don't need it in the box. And then for 10%, it was 10.42. 10.99 for the 20%, and 11.55 for our highest concentration. Okay, the volume of each of these things. We were reading from the bottom of the meniscus. It was right on the line. So if it's right on the line, I don't know if you guys can see that. It's right on the line. I can read the 10. If it was below that, it would have been 9.8. But because it's right on there, it is 10.0. So that's going to be our volume. Okay. And it's recording it as just 10. For the density, this is a handy little trick. I'm going to enter an equation here. So when I hit the equal sign, now it's ready for me to input an equation. And we know that density is mass over volume. So I'm going to hit the mass box divided by the volume box and hit enter. And that is the density, 1.011, which makes sense because water is 1.00. And since we added 5% salt, it's just slightly higher than that. Now, if I go over to the corner of the box until I get the cross symbol, I can drag that to the right, and that's going to copy this equation for each column. And I automatically have all of the densities done. Okay, we need to graph this data for the last part of the procedure. And we want, on the x-axis, we want the one that we are manipulating, which is the concentration. So I'm going to create another table. In fact, let me put in my grid lines here. And I'm going to create another table that has my x and y values. So I have concentration. I'm going to put the units because this is going to go into the table. concentration in in percent. Okay. And then I have my dependent variable, the one that depends on what we are manipulating, which is the density, okay, in grams per milliliter. Okay, so my concentration, I have, these are nice and easy, 5, 10, 20, and 25. For my densities, 1.011, 1.042, 1.099, and 1.155. Okay, so let's highlight all of this, and we are going to come up to the little plot right here where it says insert chart. I want a chart. We're going to do a scatter plot. It's thinking about it. There we go. Ooh, and we can see a nice trend here. We don't need any of these densities down here, so let's go in and fix this a little bit. So notice it already labeled the axes for me because I put them into the top of the chart. Got it. Let's customize. I don't like the title. Okay, this is density. I'm going to call it densities relationship to concentration. Oh, and of course it got all weird. Nice. Densities to concentration. Get rid of all the other stuff. Densities relationship to concentration. Extra space there. Okay. So that looks a little bit better, but I don't like all that dead space at the bottom. So we are going to, let's move myself out of the way. Get out of here. Okay. That would be on the vertical axis. This line, label. You know what? We do need more lines in there. Oh, here's the minimum, maximum. So the minimum value, let's set that to 1.00. Now we can see it a lot better. Okay. And you know what else? This should cross at the 0 line. Okay, so 1 exactly should be 0. Doesn't look like that is the case. I am going to axes. Is it the legend that gives me, or series? Right here, we want a trend line. There we go. And you know what else? Setup. I kind of do not want a line chart. That's the problem. I wanted a scatter plot. Line, column, pie, scatter. Scatter plot is what we wanted. There we go. Much better. Now I have my trend line, so I changed the chart type to scatter, which is what I should have selected in the first place. Series, trend line. I want the type to be linear. Okay, that is correct. Whoops. I want the trend line. Show R squared value. And use equation. Okay, so under the label, we want the equation for our line right here. We want the R squared value. The R squared value tells us how close we are to a straight line. 0.99 is very good. 1.0 would be exactly a straight line. 0.98 is acceptable. Okay, that's a pretty good R squared value. We're pretty close to a straight line. You can see that one is a little too low and one is a little too high. So we have some kind of error in our lab. It's not perfect. Okay, and other than that, I believe that this looks good. Okay, so we are done with our graph here. We have our data table. Can I move you out of the way, graph? Normally, there we go. We can select it, move that out of the way. Okay, so in our lab, we are going to want our results in a data table, which I have done for you, and you're going to want to make a graph, which I've also done here. So you guys will have to take the data and do your own graph and your own charts, okay? In order to find the identity of our unknown solutions here, we're going to need either this equation or we're going to need some more grid lines in here. So I'm going to double click my graph, and I need, in the horizontal axis, log scale, where's the minor? Let's see, grid lines, there we go. Grid lines, major grid lines, we want minor grid lines as well. Looks good. And we also want these for the horizontal axes, show the minor grid lines as well. And that will give us a lot more information over here, so that when the question says, let's pretend the density was exactly 1.10, how would we find that concentration? If the density of our unknown is 1.10, then we're going to follow that 1.10 over to our line, and you can see where it crosses right here in between the 15 and the 20. Okay, since I added the minor lines, so between 15 and 20 is 5 over 3. This would be 17 and a half. I'm going to say 18. 17, 18, 19. That's a really weird number. I'm going to guesstimate that it's about 18. Okay, so we could do the math mathematically with our calculator to figure out what that is. But if I said 18, I know it's between the 15 and the 20, so I can estimate the concentration. Now, if I took my Y value and I plugged that into my equation and I solved for the X value, then I would have the exact concentration in percentage. Okay, so that's how we're going to find the concentration of our unknown solution.